that could be this guy. That was pushed. I'm not so sure now. Okay, if I go to main, oh no, it's okay. Yeah, I fixed it. The detached head was the problem that I had. Okay, so now I should be able to see the demo. Yeah, because I remember I saw this problem and I fixed it. Okay, now I can see it. So next week, we're going to start talking about the clock. Okay? But before we talk about it, let me just bring up the lessons that we have for the clock. The clock system, it's all in the RCC chapter, okay? And we've been already using this, and it stands for reset and control and clock control, okay? So we've been already using the RCC because when we are connecting things to the clock, when we're doing this, right? That's the module, the RCC is the clock module. So we're connecting the peripherals to the clock, okay? Now, before we can understand the clock, how much time we have? We're gonna have to, yeah, 10 minutes. I'm gonna use the 10 minutes, sorry.
15.
Yeah, sorry, because this time is essential. But anyways, so the clock to work, it needs some sort of source, oscillator, okay? And this clock system has many oscillators, okay? And they're all labeled like this. And for example, the HSI stands for high speed internal, okay? What do you think the HSC stands for? High speed external. What about the LSI? Low speed internal. So it's very self-explanatory, except for the PLL. Now, how do we really make sense of this? In the demos, I think I put one of these QMX files, the Nucleo 64 sample. Hopefully that works. Yes, these files can be saved. And where we can look at the clock is in this tab here. Okay? Now these, I'm gonna reset the defaults. How can I reset to defaults? Come on. Oh, it's because it's using. Interesting. Anyways, so all these high-speed internal, high-speed external, they're all listed here. And what does this symbol mean? What is this?
Multiplexer.
Multiplexer, excellent. It's a MUX, where you encode can select which one of the oscillators you want to use for your clock. Now, what we have selected right now is the default mode, which is why our clock is running at 16 megahertz. And all this time, you just had to believe that what I said. From this point on, probably after Monday, you will be able to verify yourself that what I'm telling you is true, that this micro is by default running at 16 megahertz. And it's because it's getting the oscillator from the high-speed internal, which is 16 megahertz. So it's an internal oscillator. But there's also an external, okay? That's 8 megahertz in this particular case. There's also a lower speed external, which is a crystal. Anybody familiar with a crystal oscillator? Have you ever seen one?
Yep.
Have you in any of the other courses that you're taking? Or?
No, just for emulation purposes.
Yeah. So let me show you what a crystal oscillator looks like. So normally when you're seeing things like this, right, those are crystal oscillators, although you may see some other different footprints. So I'm going to show you later on the board where the crystal oscillator is, okay? And The lowest speed external uses a crystal, therefore is a very accurate oscillator. The best source of an oscillator is a crystal oscillator. And this particular external, low speed external, is 32,768 hertz. Why such an odd number?
$32,768?
That sounds like why is not 32,000, first of all?
Gotta be some sort of like log scale or something.
Yes, this is 2 to the power of?
13.
13? A little bit up. 2 to the power of 15. Yeah. And the reason for the crystal oscillator to count in binary is so it can be super accurate. That's the whole point of this. And typical applications for a low speed external is an RTC. Does anybody know what an RTC stands for?
Real-time clock.
Real-time clock. Anything that has a real-time clock needs a crystal oscillator. Why? Obviously because when you turn off the thing, you want the time to keep going and do not get out of sync. Okay? Now, in order to keep this thing going when the power is off, most likely you need a coin cell battery. Obviously, we don't have that
Or a watch battery.
in this board. That's why we cannot use the RTC. But in other boards, you will have that. Now, can anybody recall anything that you've ever seen that has an RTC and a coin cell? Your watch.
A watch would, old cartridge-based games that had time-based events would need an RTC with a coin cell battery. And we have to replace them every 20 to 25 years for that real RTC to still be there.
One other thing, the most typical one. I can tell you with confidence that in this room there are at least 24 RTCs and 24 coin cell batteries. 25.
Yep.
Huh? Not everybody has a phone. Yeah, but the phone has an RTC as well. But I'm talking about something else. Look around.
Computers.
All the computers will have
All the
one.
computers. Who in here built his own computer? Okay, when you look at the motherboard, have you seen that coin cell battery? What happens when you remove it?
The BIOS gets very angry at you.
The BIOS gets reset because all the settings of the BIOS need that coin cell battery to be kept. Moreover, the RTC that is on the BIOS needs the coin cell battery. In fact, when you remove the coin cell battery and put it back, and you enter the BIOS of the computer the first time you boot out, you're gonna see the time as 0, 0, 0, and whatever, and everything goes back to 0. Because the way your computer can keep the time when you turn it off is by keeping that in the RTC. That's why it needs a coin cell battery. Of course, nowadays things are more modern because you have internet, right? So the computer connects to the internet and it synchronizes the time right away with the network. But before, when you didn't have internet, the computer still could have the time correctly, even when it turns off for several days. Okay? So for that level of accuracy, you need this crystal, and we do have one of these on the board.
Between X2 and X3.
Yeah, so it's one of those. The X3 is not populated because it's using an oscillator that is coming from the other micro, from the debugger micro. Now, oscillators can be digital or crystal, but the crystal is more accurate. Okay? So, what we're going to do next class, we're going to learn a way, because so far I think we've been using this for a while to output the system core clock, right? And we did say that this variable is actually part of the CMCs and it's in the background. I can show you next week where does it come from, where does it get updated. But if we print this variable, most likely we're going to print 16 million because the clock is running at 60 megahertz by default. Okay. However, we're going to do something more. It talks about the same thing that I was just talking about here. This is a diagram of the clock. How do we verify the clock speed? Please read this lesson over the weekend when you're bored at home, unless you're watching the F1. That would be very interesting. That would be the only case I'll forgive you for not reading this. Okay? But there's one way of checking the system clock, which is using this variable, right? That's the software application. There's a hardware application. There's a way of outputting the clock speed on a penny. And that's what we're going to experiment next class. And for that, we need to enable an alternate function. So we're going to show you next class and how to see the clock speed on a penny.
So function low.
Yeah, and the alternate function, well, if you copy paste all this code, you should actually be able to see it on that particular pin. In this case, I think it's PA8.
PA8.
Yeah. So there's a possibility, and for the alternate function that you need to set is 0. You don't have to do this manually. You have your alternate functions already coded.
Oh, because you're going to 8, so yeah, it's AFR high. Okay.
And what we're going to learn next week is about using the PLL, which stands for phase lock loop. We're going to learn about that and how to actually multiply that frequency to go all the way up to 64 megahertz. So the clock is going to be the next topic that we're going to be covering for the next maybe couple of weeks or week and a half. And then after that, we're going to jump into the final topic, which is timers. Okay? And more. Thank you for your attention. Oh, I used all the time. Perfect.